Bismillahirrahmanirrahim. Assalamualaikum and good day. My name is Nurul Najiha binti Muhammad Huridin. I am from 4SKMT and that is Aeronautic, Mechanical Engineering Aeronautic. My title for undergraduate project 2 is Performance of Gasifier Chamber Unit by Using Agricultural Waste. My supervisor is Dr. Najiha binti Osman and my co-supervisor is Professor Dr. Muhammad Nazri bin Muhammad Jaafar. Let's take a look at my presentation outline. First, we'll go through the introduction, a little bit background on gasification, and then we'll see my literature review. Next, we'll look through methodology, and then we will go through results and discussions. Lastly, I will talk about the conclusion and acknowledgement. In introduction, there will be 5 things that I will cover. One is the background of study, and then the problem statement, objectives of this project, the scope of study, and last but not least, the significance of this study. So, what has happened that made this study relevant? Here is my problem statement. First, the Department of Environment in Malaysia has discouraged the open burning of biomass waste. This discouragement has caused a lot of profusion of processing waste created especially in the agricultural sectors. So it will be more beneficial if we could somehow use this biomass into renewable energy. And then this study will make use the process of gasification in order to address the agricultural waste, especially one from palm oil industry. Moreover, it will enable gasification to obtain higher acceptance in this industry. There are 3 objectives of my study. One is to determine the context of feedstock by using the proximate analysis. Second is to investigate the ability of numerical simulation in the gasifier chamber unit. And third is to determine the flow characteristics via simulation in the gasification system. There are 4 scopes of study in my undergraduate project. First, I will analyze the proximate data for feedstock. There are 5 samples in total. One is the palm kernel shell, the ground coconut shell, torrefied rubber seed, empty fruit bunch, and wood chips. Second, computing the fixed bed chamber unit for swirling flow in reactor chamber. Third is the computing of inlet velocity will only focus at 9 meter per second of speed. And the fourth one is simulating the flow for 3 swirler type inside the reactor, and that is the 30, 40, and 50 degree. The significance of my study is that one, it will potentially contribute to give fundamental study on the impact of what numerical approach will be doing onto renewable technology establishment, especially in Malaysia. Second is to address efficiency and performance issue of numerical simulation, especially in biomass combustion. This is my Gantt chart for UGP2. There are slight changes in this chart due to the pandemic outbreak. The initial plan was to first start out with experimental till the end of the semester. However, due to the COVID-19, I have changed the plan to computational approach. I will explain this later on. Now, on the literature review, there will be 3 main topics that I will cover. One is the gasification, and second is the type of gasifier, and lastly is the biomass itself. According to Broad 2010, gasification is a chemical process converting carbonaceous material into useful convenient gaseous fuel, which include chemical compounds such as carbon monoxide, hydrogen, and carbon dioxide using incomplete combustion. There are 4 main steps in the gasification reactor itself. One is the oxidation, second is the drying, pyrolysis, and then the pyrolysis. Last but not least is the reduction. 3 main types of gasifier is infamous in this study. One being the fixed bed, fluidized, and then the rotary kiln. In this study, we are going to focus on fixed bed. Well, fixed bed has two technological solutions, the updraft and downdraft reactor. It has a simple construction and have high thermal efficiency. Now, more on biomass. Biomass can be converted to electricity, heat and fuels via biochemical or mechanical extractions and also thermochemicals such as pyrolysis, combustion and gasification process. The gasification of biomass is one of the most reliable process assignable to its high energy efficiency. Gasification is the sole process that converts biomass into synthesis gas. Summarizing most of the readings that I've done for CFD of biomass gasification, one of them is Davamani in 2015 has said that there are three main parts of carrying CFD in biomass gasification. One is basically the software modeling, second is meshing, and third is input parameter or simulation setup. Well, it also proven written also by Chodo, Pennedy, Sanker and Reddy in 2019 saying that K-epsilon turbulence model is one of the most reliable model to be implemented into gasification. Summarizing some of the literature review, most of the CFD studies that have been done mostly focus on the input parameters of the simulation itself, and not on the physical parameters differences of the reactor. After preliminary study has been done during UGP1, works are proceeded into two. One is the experimental study and two is the CFD analysis. After all been done, results will be collected and validated and then transferred into thesis writing. First step that has been taken for experimental work is the characterization of biomass materials. This process will enable us to know the calorific value of each sample that we are going to use. Well, this is the picture of me using bomb calorimeter in UTM combustion lab. The study of proximate analysis will enable us to know the moisture content, volatile matter and ash content inside every samples that we are going to use and later on be put into simulation parameter. Well, this is the three steps. It has to go consequently. The first steps to proximate analysis experiment is to first make sure the samples that we have are turned into fine powders or as small as we can get it. Well, the picture with a ruler, a scale, is the torrefied rubber seed, and next to it is the wood chips being sieved to gain the powder. This is me putting samples into furnace for proximate analysis steps. The plan was to proceed with gasification right after proximate analysis has been done, while the rig has even been prepared. Unfortunately, this must be stopped due to no one is allowed to be in UTM compound during the outbreak. The situation has forced us to change the scope of study and take an alternative step. The alternative step is going through computational analysis using ANSYS Fluent. Well, first of the step is to do a 3D modeling. This is the swirler that will be assembled inside the reactor. There are three angles of swirler that we are going to test: the 30, 40 and 50 degree. As you can see from the slide, this is the reactor modeling. There are 4 air inlet at 90 degree and also 1 outlet. Well, if you're asking where is the swirler, it would be at the 0.6 or 5.95 millimeter height. The picture on the left shows the airflow during gasification process. The air will go through the inlet valve at the bottom of the reactor. The biomass will be fed in at the top of the reactor, and once the air is cool, it will go through the outlet valve. For simplicity purposes, during simulation, the picture on the right is generated. This eliminates the unnecessary parts that shall not be included during calculation. After modeling comes the meshing parts. As you can see, I have generated a meshing on 5 bodies. It contains 2 types of mesh. That one is hexahedral and tetrahedral. Nodes that I've generated is 100 and 1333, and also 309,506 elements. This may seem small, but it has generated a good quality mesh element for this reactor. It is important to set boundary condition before running the simulation. This is my boundary condition for the experiment. From the simulation, I was able to generate 4 results. One is the proximate analysis from the first experimental test, and the rest of the 3 is from simulation itself. This is the result for proximate analysis. As you can see, only the ash content for torrefied rubber seed is exceeding the normal or typical limit. This may be due to mishandling of sample. The residuals are simply a function of model error. Lower residuals mean a better quality solution. It is also worthy to note that it is possible to have a fairly high residuals due to local effects, but still able to have a decent overall solution. Due to time constraint, the simulation was not able to reach convergence just yet, hence producing such vibrating residuals values. In order to understand the residual percentage better, I have put the data into a graph of a percentage against time of 1 hour of combustion. 40 degree and 50 degrees were chosen because of its quality outcome. From the figure, it can be seen that the carbon dioxide in a red color composition has increased when the amount of steam entering the system increased with time. This is the result of water gas shift of between carbon monoxide and water producing carbon dioxide and hydrogen occurred with the equilibrium balance to the right. These are 4 main reactions occurring during gasification process. The one I just mentioned just now is the 4th equation, making sure that carbon dioxide and hydrogen is produced at the outlet of the reactor. Observation made on particle path lines will enable the visualization trajectories that individual fluid particles flow. From these figures, it is clear that different swirler angles cause particle distribution to differ from one another. From the figure, particle path lines for reactor with swirler 30 and 50 angle shows a rather similar path line. However, swirler with the 50 degree has circular motion of particles, and this is how Basu in 2013 has described the movements of solid particles during combustion, where it is dragged upwards with the airflow. Results from simulation shows a somehow accurate combustion process where the reactor shows much higher temperature at the air inlet and gradually cooled down, reaching top of reactor as it reaches the drying zone. However, swirler 40 degree and 50 degree swirler presented a relatively same theory to simulation result. The immediate temperature will drop down once it gets to the grate. It's certainly how Chowdhury and Molbalkar published in their paper. We have now come to the conclusion of this presentation. Besides the proximate analysis, on the CFD analysis itself, there are 3 things that we can highlight. Evaluating the residual percentage across 1 hour of gasification, it has been found out that reactor with swirler angle of 40 degrees shows a similar gas composition increment to existing studies obeying the gas reaction of combustion phase. Next, particle path line is seen to be in correct motion with the use of swirler at angle of 50 degree, while the other disperse accordingly to each phase. Only those at 50 degree move along the airflow motion. Lastly, reactor with angle of 40 degree has the most accurate static temperature distribution, where the air is immediately cooled to 1073 Kelvin at the combustion zone. In conclusion, reactor with swirler of 40 degree come out as somehow an ideal swirler for gasifier, set and it satisfies the residual composition and static temperature distribution. Here's some recommendation if this work would be done in the future. One is to resume with the experimental work. A lot of past studies has shown that it is better to practice experimental and simulation work hand in hand to produce a much more credible results. Second is to simplify the modeling. In this experiment, I have generate 3 different parts: the top, middle, and the bottom of reactor. Probably, if I have chosen to create one simple reactor with less surface, it will produce better results. Of course, I would not have been here if it's not because of these amazing people. Firstly, I would like to thank my supervisor, Dr. Norazila binti Uthman, for all her dedicated guidance and support, for always pushing me to do my very best. And next is the combustion lab team, especially to Encik Roslan Rahim for from the beginning of my experimental work to the very end of it. Next is my CFD mentor. If it's not because of Encik Aizat Salim, I would not be able to understand the simulation process in such short amount of time due to the change of scope. Next is my aeronautic comrades. Thank you for always being here from the early starts of my studies until today. And last but not least, of course, to my family member, especially my mother and my brother, for giving for their prayers and tremendous support. These are some of the references I have used in my studies. That's all from me. Thank you.